everyone. Looking at the last topic called the binomial theorem. First thing we want to do here is just do a little exercise of expansion. If we take a binomial called x plus y, raise it to the second power, this means that we are taking x plus y times x plus y, which will equal x squared plus 2xy plus y squared after we are done foiling. Now, if we look at x plus y to the third power, a further expansion, all right, this can be separated as x plus y multiplied times x plus y to the second power, right? Again, we are taking x plus y times x plus y times x plus y, but I'm going to group two of these x plus y's together because we already know what x plus y squared is equal to. It's equal to that right there. So let's take this is going to be x plus y times x squared plus 2xy plus y squared. So this is distribution. We are distributing x into this trinomial, and then we are going to, after that, distribute the letter y, the variable y, into this trinomial. So let's take a look. We're going to need some space here. We're going to get x to the third plus 2x squared y. All right, that's going to be x times 2xy is going to be 2x squared y plus xy squared plus x squared y plus 2xy squared plus y to the third power. Again, we distributed x into here. And then we distributed y to get those three terms. Now let's combine like terms, right? It looks like over here, x squared y and x squared y are like terms, and xy squared and xy squared. So the reds and the blues are going to match up together. X to the third plus 3x squared y plus 3xy squared plus y to the third power. Now let's do this one more time, this time with x to the fourth power. And just like before, we can take x to the plus y to the fourth power and call this to be x plus y times x plus y to the third power. Again, the rules of exponents are going to apply here, basically with x plus y as our base. And this visible 1 plus 3 is equal to 4. That's how we're getting this. So this is going to be this binomial of x plus y multiplied times this expression over here, which I will copy and paste right into there because they are literally the same. So now we're going to do distribution once again. We're going to distribute x into this entire expression. Then we're going to distribute y into this entire expression, and then we are going to combine like terms. This one is going to get longer. X to the fourth power plus 3x to the third times y plus 3x squared times y squared plus x times y to the third power plus x to the third times y. So once we are done here, we have distributed all the x's. Now we're going to distribute all the y's. Distribute all the y's. X to the third y plus 3 x squared y squared plus 3xy to the third plus y to the fourth. And we can combine like terms once again. X to the third y and x to the third y are going to combine up. X squared y squared over here, x squared y squared, those are like terms. And let's look at, let's use green, xy to the third, and here xy to the third. So now three separate like terms to add up together. X to the fourth plus 4x to the third times y plus 6x squared y squared plus 4xy to the third plus y to the fourth power. And this is the expansion of x plus y to the fourth power. And this is the expansion of x plus y to the third power. And then we saw over here the expansion of x plus y raised to the second power. Now this was quite a long exercise, especially xy to the fourth. X plus y to the fourth was kind of long. So there exists something called the binomial theorem. The binomial theorem is a method of expanding a binomial raised to the nth power. So we can take a general case and we can apply this to any number. And here's the process, right? This is not really a formula that you memorize. This is more of a process that you memorize. X plus y raised to the nth power starts off with this right here that I will circle. We'll talk about this, right? This is called a combination in mathematics. The branch of mathematics this kind of really is mostly used is in probability, but it is a function that is useful here. It's called a combination, and the way it's read is the top number, choose the bottom number. This is not a fraction, right? Do not put a fraction line in between. This is called here n choose 0, and n will be an actual number once we get down to the practice of it. So we're going to have n choose 0, x to the nth, y to the 0 power. Again, anything to the 0 power is equal to 1, but we're putting it in here for display purposes, really. Because look what happens on the next term, right? Let's compare the first two terms here, and the terms are separated by these plus signs. In the combination, n stays the same, and as you go from one term to the next term, you're increasing that choose number by 1, so from 0 to 1. The base value here, x, stays the same. It's whatever that is in your binomial, the first term of your binomial. That's what x kind of represents here. It started out being raised to the nth power, so the same number as this. And then as you move on to the next term, that value, that exponent, decreases by 1. Right? So we're going from x to the nth power over to x to the n minus 1 power. The second term in this binomial is the letter y. For this one, again, this is a general case, so this is the variable y. It could be a number, it could be another variable. Starts out with y to the 0 power, and this one increases by 1. So it goes from y to the 0 over to y to the 1. So if we follow this format, again, this choose going up by 1, the next one, again, after this plus sign over here, we're going to have a new term, and this choose number is going to go up by 1 again, in this case, n choose 2. The exponent of the first term is going to decrease by 1, in this case, n minus 2. Because remember, what started at n goes to n minus 1, and then now is at n minus 2, and we are at the same time increasing the exponent of the second term in this binomial, y to the 0, y to the first, and now this becomes y to the second. And this process of increasing the choose number by 1, decreasing the first exponent by 1, and increasing the second exponent by 1, this continues on and on until you reach the choose numbers being the same, n choose n, until that first exponent goes down to 0, and at the same time, that second exponent should go up to n. Right, so what you're doing is writing out the entire expansion with this process of increasing these numbers by 1, decreasing other numbers by 1 at the same time. And at all this time, some things should be constant, which is that the sum of these exponents must equal n. N plus 0 is equal to n. 0 plus n is equal to n. 1 plus n minus 1 still equal to n. All of these numbers, all of these exponents should add up to n at all at the same time, right? You're still having the same base values, x and y in this case, moving forward. So let's take a look at x plus y to the 4th power. We did that already, but let's take a look at how this is going to go. We're going to start with, over here, n is equal to 4 because that's the exponent here. That's going to be 4 choose 0, x to the 4th power, y to the 0 power, plus 4 choose 1. Again, we are taking this bottom number, this choose number, increasing it by 1. We're taking x was to the 4th power, now is decreasing by 1, going to the 3rd power. We're taking y was 0, increasing by 1, that's y to the 1st, plus 4 choose 2, again increasing that by 1, x squared, y squared, taking these numbers, decreasing 3 minus 1 is 2, 1 plus 1 is 2, and then we are taking the next term, 4 choose 3, x to the 1st, y to the 3rd. Again, notice the trend of these numbers, the first exponent, and the trend of the second numbers, the second exponent there, plus 4 choose 4. Now, our choose number and our top number match up, so we know that we are going to be finished here. X to the 0, and finally y to the 4th. I just made that space in there. So again, we know we're finished here because this first exponent is equal to 0. It cannot decrease anymore. All right, so that's how we know that we are done. And if we evaluate this, again, I will teach you how to evaluate these 4 choose 0 kind of thing. 4 choose 0 is equal to 1. Y to the 0 power is equal to 1. 4 choose 1 is equal to 4. 4 choose 2, this is equal to 6. 4 choose 3 is equal to 4, and 4 choose 4 is equal to 1. In addition to that, x to the 0 power, again, anything to the 0 power, is equal to 1. So this ends up equaling x to the 4th power plus 4x to the 3rd times y plus 6x to the 2nd times y to the 2nd. All right, we're over here right now in our simplifying process, plus 4 times x times y to the 3rd plus y to the 4th after we clean this up, because 4 choose 4 and x to the 0 are both equal to 1. So we end up with this expansion right here. Same thing that we got before, right over here, but maybe slightly faster. So I hope that helps to kind of bring home the process, because again, using the binomial theorem is a process. But the real magic of the binomial theorem is it allows us to not only write out this entire expression. It allows us to jump to certain expressions. It allows us to kind of ask, what's the 3rd term going to look like? What is the 6th term going to look like, right? Without having to write out the first 5 terms, we can jump straight to the 6th term in this sequence. Now, before we do that, I do want to go over this combination real quick. And if we are covering combinations, we have to talk about something called factorial. Factorial is this symbol right here, because the definition of a combination which can be written like this, but can also be written with a large C and two smaller numbers kind of in the subscript, right? This notation, n choose k, is the exact same as this notation, n choose k. The notations mean exactly the same thing, and you will most likely encounter both types of notation in your math travels. But the first thing we have to talk about here is something called factorial. That's this symbol r with an exclamation point afterwards. This means r times r minus 1 times r minus 2 times r minus 3, and so on and so forth. How do you know when you are finished? When you get down to 1. So if we want to calculate, let's say 5 factorial, this is going to equal 5 times 4 times 3 times 2 times 1. And multiply this all together, 20 times 6 is equal to 120. So if we follow this formula for a factorial, let's say 6 choose 2 is going to equal 6 choose 2. Either notation is fine. Right, this is going to be equal to 6 factorial divided by, following this formula here, k factorial, which is the number on bottom, factorial, and then 6 minus 2 factorial. So if we write out all our factorials, 6 times 5 times 4 times 3 times 2 times 1. And this is equal over 2 times 1, which is this factorial. And this is going to be equal to 4 factorial, because in the parentheses 6 minus 2 is equal to 4. So that's going to become 4 times 3 times 2 times 1. Now the thankful thing, instead of having to multiply all this stuff out, the nice thing is that this is all multiplication, so these can be canceled. 4 times 3 times 2 times 1 can be canceled on top and bottom. So we are left with 6 times 5 over 2 times 1. And once again, we can reduce here. 6 over 2 can reduce to 3 over 1. And 3 times 5 is equal to 15. Now, we do want to mention one other thing. Right, this is how you calculate a factorial. Factorial can be calculated in a faster way. Let's remember that 6 choose 2 is equal to 15. Right? In class, we use calculate 84 as our kind of preferred graphing calculator. And this calculator, it's basically a TI-84 simulator on my iPad. But if I hit the math button, underneath there's second and alpha and then the math button over here, you get a bunch of menus, right? Get the option to raise to the third power. You can, choice number 5, you can do a different numbered root. But if we move over, hit the right button, and you'll be able to do this on a TI-84 also, go to PRB, probability, you see an option here, number 4 for factorial, but you also see an option for NCR, which is a combination. Now we're going to hit enter. And we see that our cursor is, sitting kind of right before. So if we put the number 6, hit the right arrow, and then hit the number 2, take a look what we have. We have 6 choose 2 in here and hit enter. This is equal to 15. This is a very quick way to calculate all of the different combinations that you're going to need to calculate. Right, so moving forward, I'm going to calculate all my combinations this way. I'm not going to show it. They're all, I'm just going to write down the numbers, but again, you can jump to this calculator in order to do that. So let's look at one more thing, which is something called Pascal's triangle. Now, Pascal's triangle is a fun little thing made with numbers, right? One thing about Pascal's triangle is the top is called row 0. Underneath it, row 1, row 2. And in order to get to the next row underneath, right, in order to populate row 2, we are essentially adding the two numbers that are above it diagonally. On the edge, that means just the number 1 because there's nothing else to add. In between here is the number 3, which comes from 1 plus 2. Another 3, which comes from 2 plus 1. And then we can finish off with a number 1. This is row number 3. Let's move down to row number 4. We're going to have a 1 on the edge. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And finish that off with a 1. Let's move down to row 5. That's 1, 5, 10, 10, 5, and 1. From beginning to end, again, we are getting these numbers by adding the two numbers diagonally above each entry. So what's happening here is that this is going to be a triangle because we're seeing it getting larger and larger. We're seeing these rows get bigger and bigger. Let's calculate row number 6 to finish this off. But again, this triangle can go on forever as long as you need it to. Start with 1, get 6, 15, 20, 15, 6, and then 1 at the end. Now take a look at these numbers, this coefficients, right? Let's take a look at this one right here, which is row number 4. 1, 4, 6, 4, 1. I am going to actually copy this row. This is row number 4. And I'm going to paste it right underneath here. Right? This is row 4 of our Pascal's triangle. And what do we notice about that is coefficients are all the same. And in addition to that, remember, this was row number 4. And this was the expansion raised to the 4th power. Right? So there is a correlation here between the numbers that you see in Pascal's triangle and the coefficients that you're going to see on a binomial expansion of any number, really. But the caveat is that the top has to be declared as row 0. That's why I called it row 0. Right? In addition to that, if we call this 0, 1, 2, 3, 4, 5, 6 terms in here, 6 choose 2 ended up equaling 15. Remember when we calculated this, either calculated it by hand or we put it into the calculator. 6 choose 2 was equal to 15. So again, there is another correlation there between these numbers. So that's a little quick thing on combinations, which is something that we will need to use when we are using the binomial expansion. Again, now like I said, the binomial expansion has real beauty in that it can be used to jump to certain terms of a very large expansion. If something is raised to the 10th or 15th power, we don't have to expand it all the way. It's going to get very large very quickly. We can basically jump straight to there, kind of like, when I watched movies on a VCR, I'd have to fast forward to a part that I liked. And then when it got to DVDs, we could jump straight to a certain chapter. It's kind of the same thing there, right? We can kind of skip all the stuff in the beginning and jump straight to the numbered term that we are interested in. So looking at the kth term in the binomial expansion, right, assuming that the expansion is x plus y to the nth power, again, x can be replaced by 5x. Y can be replaced by the number -2, and then we're going to have to do some simplification there. But it's going to start out with n choose k minus 1. Remember, this is the kth term in the expansion. N choose k minus 1. The first term in your binomial, x, raised to this power n minus k plus 1. And then y raised to this power k minus 1. Again, notice that n minus k plus 1 plus k minus 1 is equal to, if we combine like terms, k minus k is equal to 0, 1 minus 1 is equal to 0. If we add this together, this is equal to n, which again has to happen, has to equal to that exponent right there. So here's our formula, and let's use this formula to answer this question first, which is consider this binomial x plus y to the 20th power, right? So even though x plus y are, probably the simplest two terms you'll see in a binomial, even raising this to the 20th power is a real chore. Even writing out the first 8 terms to figure out this is also, it is a chore. It is tedious. So let's jump straight to the 8th term without having to write or even consider the first 7. N is going to equal 20. K is going to equal 8, which means that n minus k plus 1, which is our first exponent there, is going to be equal to 20 minus 8 plus 1, which is equal to 13. In addition to that, k minus 1 is going to equal 8 minus 1, which is equal to 7. Right, so these are the numbers we're going to need to use when we are figuring out what this term is going to look like. Because we're going to take 20 choose k minus 1, which is equal to 8 minus 1. We're going to take the first term, x, and raise it to the power of 20 minus 8 plus 1. We're going to take the second term, y, and raise it to the power of 8 minus 1. Now, I calculated these already, but I just wanted to input it to showcase where these numbers go. That's 20 choose 7, x to the 13th power, and y to the 7th power. That's doing all of these calculations right here. Now, if you take your calculator and punch in 20 choose 7, you will get 77,520. And this is x to the 13th power and y to the 7th power. And again, without writing out the first 8 terms, we jumped straight to the 8th term in this expansion. So what is the coefficient of x to the 9th, y to the 11th? So we don't actually know which numbered term this is. Not yet, at least. All we know is that it's going to have the variables of x to the 9th and y to the 11th attached to it. So the real key here is this number, the first exponent that's given. This is equal to 9. Remember, how did we get this number before? Right? We knew n was equal to 20. We knew k was equal to 8. And 20 minus 8 plus 1, n minus k plus 1 was equal to 13. So now if we know that n minus k plus 1 has to equal 9, which is this number that's given to us, we are using the same expansion, x plus y to the 20th power. So then we know that n is equal to 20. That makes 21 minus k equal to 9, right? 20 minus k plus 1 is equal to 9. Subtract 21 from both sides. Negative k is equal to negative 12, 9 minus 21. Divide by negative 1, and that means k is equal to 12, right? That means this is actually the 12th term in this binomial expansion. So now let's follow all of our rules, which is 20, choose k minus 1, so 12 minus 1, x raised to the power of 20 minus 12 plus 1, y raised to the power of k minus 1, so 12 minus 1. Right, this is going to be 20 choose 11. X to the 20 minus 12 is equal to 8. 8 plus 1 is equal to 9, so that's going to match this. y to the 12 minus 1 is equal to 11, so that matches. And now our coefficient is equal to 20 choose 11, which, when you put it into the formula, or you put it in your calculator, is equal to 167,960. X to the 9th, y to the 11th. But this problem simply asked for the coefficient, so this is all we need to box in. I hope that's good. I hope that you are able to follow what I'm trying to do here. One thing I want to do here, let's put this in a different color so that we can distinguish the beginning from the end, or the question from the solution. Right, so hopefully that's viewable for you. Let's look at something else, slightly more difficult. Number 2. Move this up because we might need some space. Let's use blue as our solution. And here we don't have just x plus y, but we're going to have 4x and then y to the 5th power. And this is raised to the power of 12. So let's find the 6th term in this expansion. N is equal to 12. That's this exponent right there. K is equal to 6. That's the numbered term that we are looking for. So that means we're looking at 12 choose 6 minus 1. We're looking at 4x, again, that's the first term over here, raised to the power of 12 minus 6 plus 1. And then we're looking at this fraction of y to the 5th power raised to the power of 6 minus 1. This is going to become 12 choose 5 times 4x raised to the power of 12 minus 6 plus 1 is equal to 7. And then y over 5 raised to the power of 5. All right, let me just put everything on the same level here. That's better. All right, that looks better. So 12 choose 5 is equal to 792. This is 4 to the 7th power and x to the 7th power. Remember, an exponent modifies what is directly beneath it. If there are parentheses involved, then this exponent will become attached to everything inside the parentheses. That's why we have 4 to the 7th power and x to the 7th power. And that same thing holds true for fractions. Right, so we're going to get 5 to the 5th, y to the 5th power over 5 to the 5th power, right? Because this 5 is going to get attached to both numerator and denominator here. So we're going to end up here with a fraction. This is going to equal 792 times 4 to the 7th power is going to equal 129,76128. This is x to the 7th power, y to the 5th power, and our denominator is going to be 5 to the 5th power, which is equal to 3125. And this is the 6th term in this expansion here. All right, that coefficient is equal to this number alone, but we're asking for the full 6th term, so that's going to have the x to the 7th, y to the 5th attached to it. If it asked for simply just the coefficient, like it does over here, then you simply just need to provide that number, not the variables to go with it. So what is the coefficient of x to the 10th, y to the 2nd? Remember, I will copy it over. This is our original binomial. We are still, on this problem, we are still working from this original binomial up here. So let's use green for this one. Right, remember, here they're not asking us for a numbered value. they're telling us the variables in here with those exponents, so we need to come up with it. Remember, n is equal to 12 based on that exponent. That means n minus k plus 1 has to equal this value of 10, which makes 12 minus k plus 1 equal to 10, and 13 minus k equal to 10. Subtract 13 from both sides, and negative k equals negative 3. Divide by 1, that means k is equal to 3. Right, which makes also k minus 1 equal to 2. So remember, our formula for this number term is going to be 12 choose k minus 1, which is equal to 2. 4x raised to the power of n minus k plus 1, which is equal to 10, right from there. And our y to the fifth, y over 5, I should write that bigger, y over 5 raised to the power of k minus 1, which is equal to 2. So let's keep on going with this. 12 choose 2 is equal to 66. You know what, let's confirm that for a minute. I'll show you how to do that again. Hit Math, PRB, NCR, Enter. And we're looking at 12 choose 2. So 12 on the left side, choose 2 on the right side, and that equals 66. I think I'm here. There I am. So 66, 4 to the 10th power, x to the 10th power, y squared, 5 squared on the bottom. Multiplying all this together, 66 times 4 to the 10th power is going to equal 692,060,16. Denominator is going to equal 25. And then we're going to have x to the 10th and y to the 2nd power. So again, this problem is asking simply for the coefficient. So then your answer is just 692,060,16 divided by 25. With the x to the 10th and y squared attached, that's the entire term. But this number here is just the coefficient. So let's look at one more. And we're going to do the coefficient here of 6x minus y to the 6th raised to the 11th power. Now, because there's a minus sign here, thus this is the first time we're seeing a minus sign in between here, this does add a wrinkle that could mean the difference between a right and a wrong answer. So be careful with minus signs. But we're going to start out the same way, which is this number has to equal n minus k plus 1. So that has to equal 6. N is equal to 11. So that's 11 minus k plus 1 is equal to 6. That's 12 minus k is equal to 6. Subtract 12 from both sides to solve for k. Negative k is equal to negative 6. That means k is equal to positive 6. So we know the value of n minus k plus 1. And now we can figure out the value of k minus 1, which is equal to 5. So let's put this into our formula, which is n choose k minus 1. So 11 choose 5. The first term in this is equal to 6x. So we're going to get 6x raised to the power of 6 from here as the exponent. We're going to get negative y over 6 raised to the power of 5, which is equal to that exponent k minus 1, right? That's how we're getting the exponent of 5. So this is equal to 11 choose 5, which is equal to 462. That's 6 to the power of 6 times x to the power of 6 times negative y to the power of 5 divided by 6 to the power of 5. This needs to be rewritten because I wrote that incorrectly. It should be negative y raised to the power of 5 on the outside of the parentheses. So something unique happening here that did not happen before, which is we have 6 to the 6th power on top, 6 to the 5th power on bottom. So that means that these can be crossed out. They can be reduced. Because if you have 6 6s on top, 5 6s on bottom, that reduces to just 6 to the 1st power on the numerator. So that's going to save us some multiplication. So we're going to get 462 times 6 times x to the 6th power times negative y to the 5th power. Right? Negative y to the 5th power in parentheses is equal to negative y, negative y, negative y, negative y, negative y multiplied by itself. Multiplying a negative number an odd number of times results in a negative number. That's how we get negative y to the 5th over there. And there is no denominator because it reduced. It reduced out. So let's multiply everything together. We're going to get negative 2,772 x to the 6th power, y to the 5th power. Right, now since again we were asked for just the coefficient, the coefficient is equal to negative 2772. So I hope this helps. This is the binomial theorem, and which again is a quick way of jumping into these expansions and without having to do all the stuff that comes before it. Again, we were able to figure out the 6th term in this expansion without writing out the first 5. All right, so thank you. I hope